Okay, so we have automatic load frequency control and automatic voltage control as the two control loops that we discussed in lesson 25. In lesson 26, we discussed the control model of the automatic voltage regulator loop, and we saw that it is a very fast loop and we are not very much concerned about the performance of this loop. So, two classes we are going to see the modeling of ALFC. Okay, what is ALFC? Automatic load frequency control. Okay, automatic load frequency control. So how we are going to control the frequency? What is the device that we are going to use here for automatic load frequency control? So when we say automatic load frequency control, we actually mean the governor. Okay, so that we are going to model. Okay, so what are the roles of the ALFC loop? Listen carefully. The basic role of the ALFC is to maintain the desired megawatt output. So ALFC means the desired megawatt output of the generator unit and assist in controlling the frequency of the larger interconnections. The ALFC loop also helps to keep the net interchange of power between the pool members at determined values that we will see when we see the two area system. Okay, that we will see when we see the two area system. Okay. Control should be applied in such a fashion that highly differing response characteristics of units of various types, hydro, thermal, nuclear, etc. are recognized. Okay, nuclear. Did you see? Okay. So you see, hydro, as he rightly said, it is very fast. Okay, so it is very fast. Whereas in case of thermal, the boiler needs to come to criticality. Okay, or critical temperature, critical pressure, all these things should come. But nuclear case, you see, we are not too much bothered about the change in frequency. Okay, nuclear power plant should always work as base loads. Once they start continue running for more than 1 year, 5 years, 6 years, like that. Okay, whereas hydro is very suitable for changing loads or changing frequency. So the ALFC loop of a hydro power plant or the governor is going to operate too often. Okay, thermal power plant also the same thing will happen, because we have already put the boiler on critical or pressure and temperature, which is known as spinning reserve. Okay, so we have got generators where boiler is already critical but generator is not yet synchronized, so that's why they also behave similar to the hydro. But in case of nuclear power plants, we generally want that the nuclear power, the load on the nuclear power should always remain constant. So here the stability is not with respect to the power system. Here the stability is with respect to the nuclear power plant itself. Because if you too much try to change a nuclear power plant, then the chain reaction can go out of control. Therefore, the news item is shared with you that the nuclear power plant has gone critical. Gone critical means it starts production, just you can say zero. Then slowly we need to increase the load, and once we achieve a particular load, we don't change. So governor is not much in function in case of nuclear power plants. Okay, so the ALFC loop will maintain the control only during normal or small and slow changes. So nuclear power plants, actually we don't want any kind of change on the frequency. It is typically unable to provide adequate control during emergency situations where megawatt imbalances occur. Okay, emergency situation, governor control cannot take care of that. For that we have stability situation. So we shall first study single area systems, only one generator and turbine. Okay, so this is one diagram that I talked to you about. This is a hydraulic amplifier based governor. So this is no longer used in modern power plants, but this gives us some idea regarding how a governor functions. And this is from the classical Elgert book, the classic Elgert book. Okay, so it is adapted by almost every textbook in power systems. Okay, so this pertains to a steam power plant. Okay, so if you see here, what is the output here? So in steam power plant, you see here steam flow. So this is the steam flow. Now if you close this gate, then steam flow is reduced. Okay, and if you open this, that is if you go below and open this, then steam flow to the turbine increases, right? Now this thing should be dependent on the flow of steam to the turbine, should be dependent on the speed or the frequency, right? Okay, so based on this linkage mechanism, so this is a linkage mechanism with a hydraulic system having high pressure oil. So this particular change in speed is converted into the up and down movement of this main piston. Okay, and hence up and down main piston, and hence the steam flow to the turbine is controlled. Okay, so as we were discussing, by seeing the speed change, this linkage mechanism will transfer the signal to this hydraulic amplifier. Okay, where this main piston will flow to open or close this gate, which will provide steam flow to the turbine. Okay, fine. Okay, now we will model these various parts of this system. Okay, so here if you see, this is the valve power delta PV, that you will see as soon as we go. So this is the explanation for the classical hydraulic governors. Okay, so we'll just go through this. The real power in a power system is being controlled by controlling the driving torques of the individual turbines of the system, by controlling the position measured by the coordinate XE of the control valve or gate in hydro. We can exert control over the flow of the steam or water. Okay, so XE is one control signal. If you are writing, you can mention in your note, XE is one signal for the control valve position. Okay, a downward small movement of the linkage E increases the steam water flow by a small amount, which if measured in the valve power is given by delta V. Okay, so XC results in the valve power, which will open or close the gates. The flow translates into main turbine power, delta PT. So this valve power increases the turbine power. Now what is this valve power? This valve power is the one which opens the valves in the turbine valves, which allows steam. Okay, very large mechanical forces are needed to position the main valve or the gate against the high steam water pressure. So therefore we use various stages of hydraulic amplifier. So what is the hydraulic amplifier? As we saw here, this is the hydraulic amplifier having this oil pressure hydraulic amplifier. Okay, so this is the valve power that actually increases or decreases the steam flow, whereas this is obtained from this linkage mechanism. Okay, so as you see here, if delta XC increases, this particular area is open. Okay, I will erase this. So if you see here, so if delta XC is drawn below, then this part is open. Okay, so if this opens, delta V increases. Okay, so delta XC of the linkage is converted into delta PV of the valve. Okay, the input to this amplifier is the position of the pilot valve. So there is another valve known as the pilot valve. Okay, the output is the main piston. Okay, the incremental movements of the 5 linkage points A to E are expressed as power increments, actually in millimeters. Okay, so this linkages say for example, when the speed is very high, turbine speed is low. Okay, when the turbine speed is low, that means this will go down. So this is the raise signal, that means raise the input to the steam. Okay, so this A, B, C, D and E, all these linkage points eventually lead to, okay, the flow of steam. Okay, the movements are assumed positive in the direction of the arrows. The governor output command, okay, so this is the final output command, delta Pg is measured in delta Xc. Okay, so that is the governor input. So if you see here, so delta Xc means this one, you see. So delta Xc means this one. Okay, so this is the governor output power. Okay, and what is the purpose? To change the steam flow to the turbine. Okay, this part. Fine. Okay. Next. Now this governor power, when it will change, so you have either a reference power change, complete change in the reference power, or there is a change in frequency. There is change in frequency due to the speed of the governor, frequency of the generator. So that is represented as delta Xg. Okay, delta Xg. Okay, main generator, which is not shown here. I think it is not shown here. Okay. Okay, then the first important equation in case of modeling the turbine governor system, write down increase. So this is known as increase. Increase in the output power results in increase in the reference power and a decrease in the frequency, isn't it? When there is increase in the output power, the generator power or the load increases, there will be a decrease in frequency. Therefore, you have this minus sign here. Okay, and this equation you write down, delta Pg is equal to delta Pref minus 1 by R into delta F. That means, why this negative sign is there? Why this negative sign is there? What I said that we have already discussed this several times, that whenever there is a load increase, okay, the frequency decreases. So because the frequency decreases, so frequency will be negative, right? And hence this term will eventually become positive, resulting in positive increase in the generator power. That is the requirement. Okay, so think about it later. The constant R has the definition of hertz per megawatt. Okay, remember this is a very important term, hertz per megawatt, and is referred to as regulation or droop. Okay, and we convert to Laplace domain having delta Pgs is equal to delta Prefs 1 by R delta Fs. So this is the first equation for the ALFC. Okay, then we model the hydraulic valve actuator. So here, as we have discussed, the final power is given by what is the generator power and how it is different from the valve power. So if there is a requirement of generator power to increase, we need to increase the valve power, and this is represented by modeling the hydraulic amplifier, and which in Laplace domain comes out to be this. So the first transfer function here is that you will see is known as the actuator transfer function, where the valve power or the power which opens and closes the gates and the generator power is related using a time constant known as the hydraulic time constant. Okay, known as the hydraulic time constant, and it has a typical area of 0.1 second. Those who are going to do project in AGC, they might require to model this in some software. Okay, now next we go to the turbine. This is the valve and generator, the relationship between valve and generator. Now we come to the turbine generator response. In normal steady state, the turbine power PT keeps balance with the electromechanical air gap power PG, resulting in zero acceleration and constant speed or frequency. Perturbations delta PT and delta PG in this powers will upset the above balance. Delta PG here is the load power that we are concerned about. So the difference in power is delta PT minus delta PG, where delta PG is the output from the plant and delta PG is the load power. Okay, and this can be modeled using this equation. Okay, how the valve and the turbine power are related. Okay, using the turbine time constant. Okay, now that I have been talking about from the beginning, that the generator power increment delta PG is basically the changes in the load that we are talking about, and hence this generator power change is the load power change. Okay, and thereafter we get this linear model of the ALFC loop. Okay, finally we get this linear model of the ALFC loop. So if you can see here, So here you have got the reference power, fine, okay. This is the governor power that is coming, the signal to the governor. This is the hydraulic valve transfer function, this is the turbine transfer function, and this is the load perturbation. And there is a change that is required to be made in the input valves, which is made through this loop. So we have only shown one part of the loop, the rest part will be closed now. And the quantity that is sensed here is the frequency, and this frequency by means of this regulation or the frequency regulation is converted into the governor power that we have been discussing. Okay. Okay. So what is static performance of the speed governor? So as I have said, static means limit s tends to 0 in the Laplace domain. So suppose the frequency is 50 Hz. So eventually the governor should result in 50 Hz output irrespective of what is the power increase or decrease. Okay. So delta F, that means final change in frequency should be 0. It should be 50 Hz. Okay. And therefore we have got this initial conditions. Okay. Delta PT0 is equal to minus 1 by R delta F0. Okay. Okay. I am making it fast. The next part is closing the ALFC loop. How to close the ALFC loop? So you need to find out something, some equation. So here some equation needs to be found out which will connect the frequency to load power. Okay, we have discussed that in our class. What we discussed, that load power is basically the kinetic energy of the turbine or the shaft or the, you can say, the rotor of the machine. So this kinetic energy is converted into frequency because of the speed, and hence we, in order to obtain this relationship between delta PD and Fs, we need to convert this kinetic energy equation. Okay, so as you see here, so how that is being made. So we solved one problem on this also. The kinetic energy is given by, is a function of the frequency. Okay, and therefore we decide a new term along with R known as the load frequency dependency, or dou PD by dou F, and hence the turbine constant will be given by, turbine power change will be given by this equation, where change in the turbine power will be dictated by the change in the load power based on the kinetic energy availability and this frequency dependency function. Okay, so further derivation, which I am not going in detail, you can go through this. Okay, so all this derivation will eventually lead to these two equations. If you see here, what was our objective? The objective was to relate the delta F with respect to this change or difference in the turbine power and the load. Okay, and that is given by this transfer function known as the power system function, or Kp by 1 plus STP, where this is the power system time constant. Okay. Okay, so I have taken this diagram directly from the book. So if you see here, we had seen this up to this part, this relationship we did not find out. So this relationship is now this system or this transfer function known as the power system transfer function. Okay, fine. So now there are some problems, so you go through the problems yourself. Okay. Okay. Now what is control area? So here control area means an area having a single frequency. For example, in our country, if you consider the whole country, that can also be considered to be a control area, provided from the NLDC perspective. But if you consider the RLDC or the regional load dispatch centers, then the state can be a control area. Okay. So far our theory was based on the assumption of a single generator feeding power to a local service area, which is very rare situation. In the strictest sense, the theory does not apply to the more common case of many parallel generators. Okay. Most power systems normally control their generators in unison. The individual control loops have the same regulator parameters. We will see a two area example in lesson 29. Okay, If also the individual generator turbines tend to have the same response characteristic, then it is possible to let the control loop represent the whole system, referred to as the control area. This can be a 2-mark question in the exam. Okay, what is a control area? Okay, so with this we complete lesson 27. Okay, so what was the output of this lesson? The output of this lesson 27 is this diagram. Okay, this diagram of the Elgert book, or the control model of the automatic load frequency control system, which involves the hydraulic time constant, the turbine time constant, and the power system time constant. Note that we have not discussed this part. This is an integral control part. We have not discussed. That's why it is in dotted line. And this part is the topic of lesson 28. Okay, so we stop here for lesson 27. Now we will move to lesson 28.